Hello dear classmates, welcome to the memory testing chapter. In the previous chapters, we talked about DFT and the built-in self-test concepts for logic testing. Now we enter a whole new topic, memory testing. So why am I learning this? Testing memory is very important because in modern designs, many memories are needed, and the memory testing concept is very different from logic testing concept. This is why we need to learn memory testing. Before we start this chapter, I have a quotation for you. The advantage of a bad memory is that one enjoys several times the same good thing for the first time. This is an interesting quotation to start this chapter. Of course, from a testing point of view, we don't want any bad memory in our system. In this video, we will first give a short introduction about memory testing, and we will introduce popular memory form models. In the other videos, we will talk about test algorithm, for simulation, test generation, and bits of memory testing. Testing of memory is crucial to guarantee the quality, and the research of memory testing has started as early as 1960s. Nowadays, memory accounts for almost 30% of semiconductor market. So that we know testing memory is very important. Here we have some popular memory test items. For off-chip test using external ATE, we can perform DC parametric test. For example, we can measure the leakage current or measure the output voltage level of a memory. For AC parametric test, for example, we can measure the rise time and fall time of the memory chip. We can also perform functional tests, for example, the march test, which can be seen in video 16.3. We can also perform retention tests to measure the retention time for the DRAM. To guarantee the reliability of the memory, we can perform reliability tests such as burn-in. We can also perform on-chip tests. For example, in our computer, our memory is protected by error detection and correction, or EDEC circuitry. EDEC performs online testing to make sure that our memory is always correct in operation. Besides EDEC, we can also have built-in self-test for memory, or even we can have built-in self-repair and diagnosis BISDR for memory. Built-in self-test for memory is particularly important for system on chip, which has many embedded memory cores that we cannot access from the outside world. This slide shows a typical memory production test flow. After the wafer has been manufactured, we perform a wafer sort. For those defective memory, we can diagnose the location of defect and repair those defects. After that, we package the chip and perform a burn-in test, and then final test. We mark the chip, followed by visual inspection, and then we can sell them to our customer. Some of the chips can be sampled by QA test. Please notice that memory testing is particularly important because we can diagnose and repair the defective chip, so memory testing can actually improve the yield. There are many types of different memories. This table shows 3 important memories. The first one is SRAM, Static Random Access Memory. And the second one is DRAM, Dynamic Random Access Memory. And the last one is the flash memory. In terms of area, SRAM is the largest. Since there are 6 transistors in a SRAM cell, the size is the largest among 3 of the memories. A DRAM cell has a transistor and a storage capacitor to store the charge. And the flash memory is the smallest one, since we only have 1 floating gate transistor, and the data is stored in the floating gate. In terms of speed, SRAM is the fastest. The access time can be less than nanosecond, and the flash memory is the slowest. Retention time means the amount of time we can hold the data. For SRAM, the data can be retained as long as we provide the power. For DRAM, the data can be leaky, so the retention time is typically less than a second. For flash memory, the data is stored in the floating gate up to several years. In terms of application, because SRAM is very fast, so they are embedded as cache or register. They can be tested using on-chip based. For DRAM, they can be either embedded on chip or they can be packaged on different modules. For embedded DRAM, they can be tested using BIST or external tester. For commodity DRAM modules, they are typically tested by the tester. Finally, the flash memory can be used as solid-state drive or USB drive. They are typically tested by ATE. In this video, we will focus mainly on the SRAM and the DRAM testing. This picture shows a DRAM functional model. When we want to read a DRAM, we will provide the address, which is decoded into column and row to access the memory DRAM cell array. The data is then amplified by the sense amplifier and then output to the outside world. When we want to write the SRAM, we will provide the data, which is then driven by the driver to write a certain cell in the memory array. Because the DRAM is leaky, so we need to refresh the DRAM periodically. Next, we will introduce useful fault models for memory. Due to the time limitation, we will focus on RAM fault models in this video. There are static fault models and dynamic fault models. Traditionally, we use scan testing for logic. However, scan testing is not applicable to test memory. What is the reason? This is a good topic for you to think about. To test memory, functional testing is commonly used. For functional testing, we need functional fault models. they are behavior models for faulty memories. For meaningful testing, we need functional fault models based on real defect, not imagination. There are two types of popular RAM functional fault models. The first one is static fault models, the other one is dynamic fault models. The static fault models include single cell fault model, double cell fault model, address decoder fault model, and etc. They are called static because this faulty behavior does not change with time. The second category is dynamic fault model, which include recovery fault or data retention fault. They are called dynamic because their faulty behavior changes with time. Please note that there are actually many other RAM fault models, such as neighborhood pattern sensitive faults, etc. But due to time limitation, we will focus on these fault models. In conclusion, different memories will require different fault models due to technology difference. Now let's look at the first RAM fault model for single cell. We have our old friend stuck gap fault, SAF. There are two types of stuck gap fault. Stuck gap 0 means a cell is always 0, and stuck gap 1 means a cell is always 1. The second single cell fault model is stuck open fault, SOF, which means a cell cannot be accessed due to broken wire. And the third one is a transition fault, TF. A transition fault means a cell fails to rise from 0 to 1, or it fails to fall from 1 to 0. In this video, we use this notation S/F to represent a fault in a cell, where S is the value or operation to activate the fault. S can be either a static 0, a static 1, or a rising transition, which is represented by an upward arrow, or a falling transition represented by a falling arrow, or either rising or falling transition represented by a double arrow. And finally, an upside down letter A means any condition. For the faulty cell, F can be either static 0, static 1, or a double side arrow represent complementation. So a transition fault can be written in this notation. When the faulty cell is supposed to have a rising transition, but the output is 0. And the falling transition fault can be written in a similar way. Now let's introduce a more complicated fault model for double cell. The coupling fault, CF, has a victim cell and aggressor cell. The value in the aggressor cell can affect the value in the victim cell. This is why we call it a double cell fault model. There are three categories of coupling fault. The first one is state coupling fault, denoted as CFST. CFST means that if the aggressor cell is in the given state, then the victim cell is forced to logic 0 or logic 1. For coupling fault, we use this notation: S1 followed by semicolon S2/F, where S1 is the value or operation to activate the fault in the aggressor cell. S2 is the value or operation to activate the fault in the victim cell. And F is the faulty value of the victim cell. There are 4 types of CFST, where this type means that when the aggressor cell is in logic 0, the victim cell will be stuck at logic 1. The second type means that when the aggressor cell is 0, the victim cell will be stuck at 0. And the third type means when the aggressor cell is 1, the victim cell will be stuck at 0. And the last one means that when the aggressor cell is 1, the victim cell will be stuck at 1. The second category is inversion coupling fault, or CFIN. CFIN means that if aggressor cell rises or falls, the victim cell is complemented. There are 2 types of CFIN. The first type means that if there is a rising transition in the aggressor cell, no matter which state the victim is in, it will be complemented. The second type can be checked in the same way. When the aggressor cell is falling, the victim cell will be complemented. In the second category, it is called the idempotent coupling fault, CFID. That means if aggressor cell rise or fall, the victim cell is forced to logic 0 or logic 1. Again, there are 4 types. When the aggressor cell is having a rising transition, the victim cell will be forced to logic 1. And the other 3 types can be examined in the same way. Now, let's have some example. Suppose we have a coupling fault CFST between the aggressor and the victim cell. When the aggressor is 0, the victim will be forced to 1. In this picture, the first column is the cell address and the second column means the cell content. Typically, there could be many bits in one address, but for illustration purpose, in this video, we show only 1 bit. If we have this fault between cell A and the cell V, when the aggressor cell is 0, this would activate the fault and the victim cell will be forced to 1. If we read the content of victim cell, we can detect the fault. Again, we show the example for CFID. Initially, the aggressor cell is 0 and the victim cell is 0. When we write a 1 to cell A, we create a rising transition. In this case, the victim cell will be forced to 1. After we read the value of V, we can detect the fault. On the contrary, if the initial values of A and V are 0 and 1, we cannot detect this fault. The second example shows a CFIN. When the aggressor cell is having a rising transition, the victim cell will be complemented. So when we write a 1 to the aggressor cell, we activate the 4, and the victim cell would be flipped. So when we read the value of the victim cell, we detect the 4. Again, for the same initial value here, when we write the 1, the victim cell would be complemented. In this case, it's changed to 0, so we can still detect the 4. Now it's time for you to work on a quiz. Consider this inversion complete 4. When the aggressor is having a falling transition, the victim cell will be complemented. Please fill in the values for these two cases. In case 1, the aggressor cell is in the first row and the victim cell is in the second row. In this quiz, the victim cell is in the first row and the aggressor cell is in the second row. Can we detect these two faults in both cases? Please now pause the video and work on this quiz. Okay, are you finished? If we write a 0 to A, then we create a falling transition in the aggressor cell. So the victim cell would be complemented, which means the good value is 1 and the faulty value is 0. When we read the value from V, we can detect the 4. On the other hand, if the victim cell is in the first row, when we write a 0 to the victim cell, we create a falling transition in the victim cell. But this falling transition in the victim cell does not affect the value of A, so the aggressor is still 1. When we read the value of the aggressor, the 4 is not detected. So from this example, we can see that the address order of the aggressor and the victim does make a difference. Even we apply the same test, the result will be different due to the address order of aggressor and the victim. Now let's have a look at the address decoder for AF. There are 4 possible faulty behavior for address decoder 4. The first one, given a certain address, no cell will be accessed. Number 2, a certain cell is never accessed by any address. Number 3, a certain cell can be accessed by multiple addresses. Number 4, given a certain address, multiple cells are accessed. It turns out that only number 4 address decoder 4 is the most important. Why is the reason? You can think about it. This picture illustrates an example for address decoder 4. Suppose we want to read address A2. And due to the address decoder 4, we also accidentally access address A1. Please note that address A1 is lower than address A2. This is because we use this upward arrow to indicate an ascending address order. Please see video 16.3 for more details. And now back to the example. Suppose we have this 4, but the contents of A1 and A2 are different. So what would the output be? Turns out there are 2 types of address decoder 4, N-type and OR-type. This slide shows 2 types of AF. First, let's consider an OR-type AF between A1 and A2. Suppose A2 is 1 and A1 is 0. If we read A2, we will get the correct value 1. But if we read A1, the good value should be 0, but the faulty value is 1. This is because the OR type address decoder 4 would generate a 1 dominant result. Now consider the N-type address decoder 4. When we read A1, we get the correct 0. But if we read A2, we get an incorrect value 0. This is due to the N-type address decoder 4 is 0 dominant. Now it's time for you to work on a quiz. For the first question, given an OR type address decoder 4 between A1 and A2, apply the following sequence. Is the fault detected? Question number 2. Given an N-type address decoder 4, please find a test to detect the fault. Now please pause the video and work on this quiz. Okay, are you done? Initially A1 and A2 are all 0. Now we read A1, we will get 0. And we write 1 to A1. And since this is OR type address decoder 4, we would read a 0 from A2. So the fault is detected. Now for question number 2, initially A1 and A2 are both 1. When we read A1, the value should be 1. And then we write a 0 to A1. And this way, when we read A2, we would get a faulty value 0. In this way, we can detect the fault. Please notice that the N-type and the OR type address decoder 4 will need opposite data to test them. As we can see in this example, initially A1 and A2 are both 0. And for the second question, initially A1 and A2 are both 1. Have you got it correctly? Now let's move on to the last fault model, dynamic fault. The most important dynamic fault is data retention fault, DRF, which means data change after a certain amount of time. There could be several reasons for DRF. For DRAM, it could be caused by charge leakage that lose our data stored in the capacitor. Or the number 2 reason, the refresh logic fails to refresh correctly, so the data is lost. For SRAM, it could be caused by a defective pull-up device inducing excessive leakage current, which changed the state of the SRAM cell. And there are also other dynamic faults, such as sense amplifier recovery fault, which means the sense amplifier is saturated after reading or writing a long stream of zeros or a long stream of ones. We also have write recovery fault, which means a write followed by a read or write at different location results in reading or writing at the same location due to slow address decoder. In conclusion, it's very time consuming to test this dynamic fault because their faulty behavior change with time, so we would need to wait or repeat our test several times. So in summary, in this video, we have shown that memory testing is very important because good diagnosis and repair can actually improve the yield. We also have shown popular RAM functional fault models, including static fault models and the dynamic fault models. There are stuck gap faults, stuck open fault, transition fault for single cell, and the coupling faults for double cells. And there are two types of address decoder fault, the N-type and the O-type. For dynamic fault, we have shown data retention fault as well as recovery fault. The fault model for memory testing must be realistic so that we can model the behavior of real defect. And we need different fault models for different memories. Finally, we have some FFT questions for you. Question number 1. We already know that scan testing is very useful to test the logic, but scan testing is not applicable to memory. What is the reason? Question number 2. Address decoder fault actually has 4 kinds of faulty behavior. In this video, we only consider number 4. The other 3 types are easy to test. What is the reason? Please explain. Thank you for watching the video.